Okay, so we continue our journey into complex analysis. I believe it was lecture 23. Let us check. Yeah. Okay, so today we'll start talking about integration and maybe, if time permits, series expansion, so on and so forth. So we already saw the issues with taking the derivative, what it means for a function to be analytic in the last lecture. So today we are going to dig into of complex functions. So I have a function. I need to integrate from the limit z1 to z2. I'm just pictorially representing this guy. Now notice I can take several paths from z1 to z2. I can take some other path as well. So the question now is which path? Uh, of course, as usual, I'll represent z as x plus iota y, and dz becomes dx plus iota dy. So that's the differential element I use in integration. Now we start from our canonical definition of a function u x comma y plus iota v x comma y. Okay, so when I integrate, I'm integrating this guy, and I just plug in the value of my differential element over here. And when I collect the real and imaginary parts, that gives me this guy. Okay, so let's see. Let me define the vector dr as dx plus dy. And what does this integral actually represent in my notation over here? Well, I can rephrase this and write this as integral z1 to z2. I'm just going to mention u, not uxy. It's againly ux vector. This is a unit vector, by the way, minus v in the direction of the unit vector vy times dr. That is, if you look at it, exactly this particular function. the dot product would be dx, that would give me u dx, and the dot product of this is going to give me v dy, this guy, plus I have similarly v plus some u times this vector dr. Okay, so that is what I have. So now just focus on this guy, for example. So this is some vector a, and this was some vector b over here. So I can write dr again as here dx plus dy, and as I notice I needed, so this was some v x plus u, well I shouldn't say uy, times dx dy dot product, and when I evaluated it gave me vx plus u dy, which was precisely the form I needed over here. But the bottom line is that this is some vector a and this is some vector b over here, and I am evaluating this integral, so I can use the Stokes theorem. I hope people are familiar with the Stokes theorem in electrodynamics. Essentially, it gives you a relationship between integral of a function over a loop, of a vector field over a loop, in terms of the surface it encircles and the curl of the same vector field. So Stokes theorem has many forms. In one of the avatars we are using, it is the relationship between a line integral and a surface integral, line integral of the vector field and surface integral of the curl of that vector field. So I have a vector field from z1, z2, and let's say I have a loop. So the Stokes integral will calculate the integral of, and let's say my vector field is defined over this particular loop. So Stokes integral is going to calculate this guy over the loop, this entire loop, the line integral, and the curl of the same vector field over the surface area, surface it encloses. So that's the idea of the Stokes theorem, giving a relationship between a integral over the loop and the surface it's enclosing. So one very familiar form of the Stokes theorem you guys already know. So notice this is the integral, or this is the evaluation of the function, over the boundary, and this is the evaluation of the derivative. Curl is a kind of a derivative operator of a function over something which is inside the boundary. A very easy form of Stokes equation you've already seen is your normal integral, fx dx from x1 to x2. That is nothing but evaluation at the boundary, fx2 minus fx1. So this was one more form of the Stokes equation, which is I integrate the function from some x1 to x2, and this is the evaluation of the integral of the function at the boundaries. That was the, by definition of definite integral. This is similar. This is some derivative is going here within the surface, and this is the evaluation of that function as a line integral over the boundary. So this is some sort of a generalization of the Stokes. So this is also kind of a Stokes theorem. So we'll be using this particular version over here. So what do I get over here? uh, I have represented a dot dl, the integral over the loop, as the integral of the curl uh, evaluated at each differential surface element. But if you look at the curl, what does the curl tell me of this function? So I had my function a as some, remember, ux minus vy, and the curl of a, if you evaluate it, that comes up to be dabba v by dabba partial derivative of v respect to x minus partial derivative u respect to y. So now if you look at it, what is this? Any clue? For this is exactly the Cauchy-Riemann condition. And if the function is analytic, this is 0. Similarly, I had the curl of b. So I was just representing this particular integral using the Stokes theorem. I have the b guy, this guy, which was v plus u. And that would precisely give me what I want. The other Cauchy-Riemann thing, which is going to be the partial derivative minus this guy. And this being 0, if the function is analytic, that means the curl of b is 0. So that means the integral I had expressed a dot dl and some iota b dot dl. Remember, this was my integral b dot dl, a dot dl or a dot dr, whatever, and that over the loop, evaluated over this entire loop, turns out to be 0 because of my ability to express the loop integral as a integral of the derivative of the surface and then of the curl over the surface and putting in the Cauchy-Riemann conditions. So that essentially means is that over the entire loop, my function fz dz turns out to be 0. Remember, fz was nothing but expressed in terms of this particular integral. So what does that mean? That means evaluated over this entire loop, if the function is analytic, I get fz dz equals to 0. That essentially means that evaluated from z1 to z2, fz dz evaluated from some path z1 to z2 plus some path z2 to z1 back over here, fz dz is equals to 0, which means z1, z2, this is some other path. This is path 1, this is path 2. So I have fz dz is equals to z2 minus z2 to z1, this integral, but I can always write this guy as z1, z2, fz dz over path 1. Just interchanging the limits again, I get rid of the negative sign, I get fz dz. So this is path 2. So I have this integral going from taking fz through one path, this is path 1, is the same as, let me just call this guy is path 2. This is the same. And notice there's nothing special about these paths. In fact, this holds for all paths. So, in other words, for an analytic function, z1, z2 integral is path independent. and the fact that fz dz over the closed loop was 0, this is known as the Cauchy-Gorsat theorem. So much so for the integrals. We know that as long as the function is analytic and the conditions of analyticity we discussed in the last lecture, then I get integrals that are path independent. So this was all for analytic functions, but can we go beyond that? So of course, one of the main points of studying complex analysis is that we will be exploring circumstances where the integrand is singular at one or more points. So for example, there is this famous Cauchy integral formula which says f0 is 1 over 2 pi iota closed loop c fz dz divided by z minus z0. So this is an example of singularity. This function may blow up at z equals to 0. So first let's study. So we are extending, see, we already know that for an analytic function, if I calculate the integral over the loop, that's 0. But what if the function is not analytic at some point in that loop? So that are the cases we are going to discuss through these Cauchy integral formulas. So when the function is not analytical, it's called a singularity. So we'll come back to this. How do we show this guy? We'll come back to this thing. But before that, let's take a short detour towards what do we mean by singularities? What is a singularity? So, well, points that are not analytic are referred to as being singular. And if a function is, so what kind of singularities we have? If a function is singular at z0, but it is analytic for z not 0, this is known as an isolated singularity. So except for z being z0, it is analytic anywhere else. So that is known as this is an isolated singularity. Okay. So one of the most important kind of singularities type of singularity is the pole. So what do we mean by the pole? So for example, let's say I have a function fz equals to gz divided by z minus z0 to the power of n. So what do I get? Let me assume n is a positive integer. Gz is analytic near z0 and gz0 is not equals to 0. So if I have these three conditions, then I say that we have nth order pole at z equals to z0. And also limit gz as z approaches z0. So in other words, I can express the same condition as, let me evaluate the limit. That gives me limit of z goes to z0 fz z minus z0 to the power of n, and let me say that that comes out to be a. So if a is a finite non-zero number element of the complex numbers, uh, then I say that I have an nth order pole. If a is equals to 0, then we have a pole less than order n, or fz is analytic at z0. Remember, fz was this guy. And if a goes to infinity, it's no longer finite, then we have a pole greater than order n. So you might need to play around and stare at these conditions a bit, but what we have done is that we had a particular form of fz, and we were exploring what are the conditions, what type of singularity we have, and we were exploring a typical type of singularity which was called the pole. And we said that if the function can be expressed as this guy where gz is analytic near z0, I am exploring near z0, n is a positive engineer, and I have the evaluation of the function at 0 not equals to 0. Well, then I say that this is an nth order pole at z equals to 0. The other way of representing the same thing is I take z minus z0 over here and I evaluate the limit as z goes to 0, 0. And I evaluate the limit a, and if a turns out to be a finite non-zero complex number, then I say that the same thing, it is an nth order pole. If a turns out to be 0, I have a pole of less than order n. So that basically means that, or fz is indeed analytic. So that is there. And if a goes to infinity, then I am underestimating. I have a pole which is greater than order n. There is something in the structure of gz which tells me that the pole is greater than order n. So let me see examples. I think one of the homeworks would be that you guys can actually think about these conditions. Do they make sense to you? Think about these conditions. So what are the various examples of these singularities? Oops. So let's consider example 1. Let's say my fz was this guy. Now we see that it's undefined at z equals to 1 and z equals to -1. Okay. So in order to see, and it satisfies, let's see, what kind of poles it has. So what I'll do is that I'll express this as what I do, limit z equals to 1, one of the points where I think that there might be a possible singularity. I write this down as fz z minus 1. Now that gives me limit z goes to 1 to z minus 1 divided by 1 minus z 1 plus z. That gives me minus 2z over 1 plus z. That gives me minus 1. So I get the limit I wanted to evaluate, this guy, to be a finite non-zero complex number, which is not 0, not infinity. So I say that it is a first order pole because the power of this guy was 1. First order pole. As in another example, I have the tan hyperbolic z, which is nothing but sine hyperbolic z over cosine hyperbolic z. This is Ez minus e to the power of minus z over Ez plus e to the power of minus z. Now, this guy is singular when, you can guess, when the denominator blows up, right? So this is Ez plus e minus z is equals to 0. So I put Ez equals to e minus z. Ez equals to e iota 2n plus 1 pi e minus z. Z equals to iota 2n plus 1 pi minus z. I'm just evaluating this equation. I just put minus 1 as this guy, e iota, and then my equation is this thing. I'm just equating the powers now, which gives me z equals to iota 2n plus 1 pi by 2. So these are where my poles are. And well, we can check if these are first order poles or not. So are these first order poles? So let's check. So I get limit z goes to iota 2n plus 1 pi by 2 z minus iota 1 pi by 2 sine hyperbolic z over cosine hyperbolic z. What is that? So I'm just plugging it, remember just the definitions. So we use L'Hopital's rule to evaluate this limit. So remember, this is nothing but I'm just evaluating the function at the value of the pole. I'm just using my way I see whether or not fz minus z0 to the power of n as limit z goes to z0. This is what I'm doing, and when I evaluate using the L'Hopital's rule, because this guy is in the form of 0 by 0 or infinity by infinity, I get the answer to be 1, which is again a non-zero complex number. So therefore these are first order poles. So this was the digression about one of the most important kind of singularities, which was the poles. In the next class, we'll again return to our friend, which is our the Cauchy's integral formula. Thank you.